joined with Akshay. And the motivation for studying this was sort of a peculiar result in peculiar phenomenon in arithmetic statistics. And so I'll just mention this thing briefly and we'll circle back to it afterwards to see how the structures in arithmetic topology help us to understand what makes the arithmetic statistics tick in this case. So I'll just record this motivation at the beginning. So the first part of my talk will be motivation and inspiration. So the motivation is this following result from Bhargava, Hankey, and Shankar. Which they obtained in around 2010. And it says the following. So it's a result in the setting of Cohen-Lancer heuristics, or in the flavor of Cohen-Lancer heuristics. And it says the following. So if you look at cubic fields, which are monogenic. And monogenic is an adjective that means that the ring of integers is generated by a single element as the Z algebra. Okay, so it means you have a power integral basis. Then for monogenics, have average two torsion in the class group. Is larger than expected. And so in fact, they sort of showed how much larger. And they found that if you look at the number of non-trivial two torsion elements in the class group, so if you exclude one, then it was exactly twice what was expected, irrespective of unit rank. And the ordering, you could have a couple of different orderings, but they ordered by sort of box height and the size of the conjugates of the generator here. So this was kind of at odds with Cohen-Lancer heuristics. It showed that you have a field that sort of doesn't obviously have much more structure, but that presents with statistics that are weird. And so if you follow the Cohen-Lancer heuristics or the Cohen-Lancer philosophy, sort of you should have objects. Class groups should behave as randomly as possible when all the allowable or all the structure that's present is actually taken into account. Okay. And so this naturally raises the question of how to fix the Cohen-Lancer heuristics for monogenic fields. So what we do is we sort of draw inspiration from sort of two stories in topology, because number fields have sort of this double identity, sort of act like surfaces, and they also act like through manifolds. And so in both cases, we'll see that there are stories that tell you that you have extra structure associated to linear forms on these objects, as long as you specify a spin structure. So first, I'll try to recall this inspiration from topology. So if you let sigma be a closed compact, a closed oriented to manifold surface, course. Then you have a natural bilinear structure on there, which is given by the intersection form modulo 2. What this map does is it takes two cycles on your surface, intersects them that are in general position, intersects them, and counts the number of intersection points modulo 2.
Sigma.
Yeah, M is sigma.
M is sigma.
Sorry? M is sigma. Ah, yes. Sorry. Just yes, M should be a true manifold always. Okay. Yes. So this is a nice non-degenerate pairing that's alternating. And so when you have a pairing, a bilinear pairing that's valued in Z mod 2, it sort of has quadratic refinements only if it's alternating, right? And so you can ask, is there a way, is there some sort of structure on your manifold that sort of distinguishes a particular quadratic refinement of this? Okay. This is exactly what spin structures do for you. So how do spin structures hold? And I'm going to tell you what a spin structure is in this setting. There are many ways of seeing them, but so they determine quadratic refinement of this intersection there. Okay, so what's a spin structure? So a spin structure here.
Can I just ask what a
Yeah.
quadratic refinement is?
Yes. Yes. Yes, let me do that first. That's a very good point. So quadratic refinement. So that means a function Q in H1 sigma Z mod 2, Z mod 2, whose polarization is exactly this form. In other words, so that's Q of X plus Y minus Q of X minus Q of Y. I think I actually want to call it omega, sorry. It's real here. Is equal to
So if we were like in characteristic not two,
yes, you always have refinements.
and the formula would be what? X wedge X, or X was just over two.
You would XX divided by 2. So yes, and so what's the spin? So I'm going to tell you how spin structures help get a refinement. So what's a spin structure? So that's a map from H1 sigma 2. So in other words, it's a map that takes framed. So this is the unit tangent bundle of your surface. So it takes framed circles or framed cycles and assigns them a parity. And you want this to be true. So if you take a small disk on your surface and you take the tangent framing, you want this to be 1. So that's a spin structure. And let's just say that sigma is equal to the unit tangent bundle. So that's a spin structure. And how do you find a quadratic refinement from this?
So it's D.
It's a small disk, sorry.
Inside U, small distance
inside
inside.
so right. So it's a small disk which you see as tangent, and then you see its boundary as tangentially framed, and that gives you an element of the unit tangent bundle.
Okay. Element or a homology class? You mean a homology class?
Yes. Because yeah. That's how do you find a quadratic refinement? What you do is, so you want to map from sort of indexed by your chi or C, sorry, from H1 to Z2. And so what you do is if you have some cycle, alpha cycle, you can take it, you can sort of lift it to the unit tangent bundle by taking sort of this is an oriented cycle. It doesn't depend on the orientation, but if you give it an orientation, sort of that gives you sort of a tangent vector field, you can lift it to the unit tangent bundle this way, and you can add you can lift it to tangent bundle this way, and you can define this particular lift. Not going to be a lift, but you define alpha total to be the sum over all the sort of simple closed curve that you have, lift them, and then add exactly m times less of the disk. Okay, these are the components when you write this as a product of sort of primes. And then this is exactly the number of primes times the boundary. So once you do this, this has a very nice property that is sort of independent of the way you've decomposed your alpha.
So this is in H1 of.
Yes. So this belongs to.
So what's M?
Sorry?
M.
Oh, so you decompose A in terms of simple closed curves. And then using this decomposition, you can lift each of the simple closed curve and then you add this.
And D here is
D is again this small disk here. Yeah, this class that sort of allows that sort of normalizes that. Okay. And once you've done that, what you can do is so this gives you something which is independent, and then you define your quadratic refinement as follows. You do omega chi alpha It doesn't mean much now, but there's a way of reading this whole story which gives you the sort of usual story that or is related to the usual way you've seen quadratic refinements pop up, for example, for Riemann surfaces. So for Riemann surfaces, there's a story of, I guess, Mumford, or even going back to Riemann, which is that you have spin structures which are really beta characteristics, and you can refine sort of the wave pairing by looking at sort of dimension of the space of global sections of spin structures modulo 2. So this is related, but this is the motion. Okay, so this story is due, quadratic refinement is due to Johnson.
what is it? Little m or boundary.
So it's m. So it's m times the boundary of B. Yeah, sorry.
And M is a number of
M is the number of, yeah. So
lifts of alpha to the.
so you'd write alpha as being equal to sum from I equals 1 up to m alpha I, where these are simple closed curves. And any cycle you can decompose as a union of them. So
The reason so that if you have some contractible curve, it just evaluates.
yeah, exactly. So if you have, it's a way of making sure that sort of whatever elements you write down is kind of sort of independent of this. That's from surfaces. So the takeaway from this is just that spin structures are useful because they determine a quadratic refinement of your bilinear structure existing on your geometrical space. So this is the first example. The second example is for three manifolds, and here, hopefully, there is a picture that's a bit clearer. So
Oh, yeah, so all quadratic refinements come differently.
you can get all quadratic refinements, absolutely. So this assignment is actually sort of equivariant under sort of shifting spin structures by the action of. So spin structures are a torsor for this. These quadratic and these quadratic refinements kind of, are equivariant under this action. So you have a similar story for linking pairing.
So alpha I with a vector thing on top of it is the same as alpha I tilde, right? Or is it? Oh, I guess
No,
you have to add
You have to
one
add-
times. Okay.
exactly. Yeah, you have to add to each sort of simple closer, you have to add one times the boundary of the
So
distance.
if an alpha I tilde is like you basically make a unit tangent vector to the path at each point. With it like that.
Yeah, this one, yes, that's right.
You're lifting it the same way you lift the boundary of D.
Yes. Okay, exactly. Yeah. Yeah. Very good. So the inspiration from three manifolds is the following. So if you have a three manifold, I'm gonna draw like two-dimensional hole in it, just to. You also have a bilinear structure, which is given by the linking pairing. So the linking is a map from 1MZ origin. Not Z. And in previous talks, we were talking about homology spheres. And so this is a different flavor of the linking pairing. It's the one on the torsion homology. And how do you define it? Well, if you have two cycles, A and B, you know that B is going to be torsion. So maybe M times B is going to be the boundary, some Seifert surface. And then you're going to define this as counting the intersection of A and S and dividing by L. So roughly speaking, you have two knots here, you can imagine. You fill one of them in, and then you count the number of times one intersects the other. So it's kind of a winding number, except you have to take into account that these are torsion. And so in order to sort of define it, you need to divide by sort of the appropriate. Okay, and that lies in Q mod Z. And this is kind of the natural bilinear structure that exists on torsion. Okay.
That's like Q mod Z and not just Q. Line Q, right?
Well, it's because it's defined on the homology, so somehow. Yeah. At the cycle level, you could do it, but and in this setting, you also have spin structures. And in the setting, they're really given by framing on the stable tangent bundle. So you can think of it as some sort of like ambient frame here. Okay. And so how does that help to define a quadratic refinement? The thing you need to do when you have coefficients of Q mod Z is specify a way of dividing by 2. And so you need to specify a way of taking of dividing self-intersections by 2. And so the way you would do it is as follows. So I'm going to try to draw a trefoil knot. Just see if I can do it. So anyways, you have some complicated knot maybe. Okay, something like that. And what you like to do is define the self-intersection. And to do that, you need to sort of push off the knot from itself so that this thing makes sense. And so how you do it is you can orient this knot that gives you sort of one thing here, and then you can pick a framing of the normal bundle that's sort of adapted to the ambient frame given by the spin structure. So this would be your spin. And so there are sort of two choices you can make for this ordered frame. And so you pick the one that matches, so that when you include it with this tangent direction actually matches this. That tells you what an even framing of the normal bundle would be. Okay. And if you pick an even framing of the normal bundle, you can push off the cycle from itself and take the linking number like this. This will be sort of independent of the choices and land in sort of once you take this piece here, it lands in sort of 2 times z. Lands in the of z, and so you're able to divide by 2. So it allows you to sort of define the self-linking number. So this is how. So it gives pushing off cycles. Okay. So
It seems like you didn't quite need a spin structure, or sorry, a framing to do that, right? I mean,
the framing of the
you said that if you have a framing of M, and then
Yeah.
you have this way of pushing off. It
That's
seems like if you just had something like what's called a P1 structure, like at every point you just had a single tangent vector rather than a full frame, would that not be enough to?
yeah, so in this case, spin structures gives you all the quadratic refinements. In this case, it doesn't. It gives you a subset. Even spin C structures would give you.
So you have to take the number of intersection points. You divide by m, whatever it is.
Yeah.
And you also divide by 2.
Uh,
Because you're doing link xx over 2.
yes.
You have an honest integer. You divide by 2m. That gives you an element of q mod z. That's the
Yes. Absolutely. Okay, so in both pieces of this analogy, so in this dual identity of number fields, if you look at both cases, you have the story that quadratic refinements are sort of, well, spin structures give quadratic refinements. And so now I'll tell you about some of the sort of analogs of the bilinear structures in number fields, and then what spin structures are, then how we get an equivalent of this story. And then I'll circle back to the statistic.
I mean, here you start with the surface, but you kind of implicitly constructed a 3-manifold, which was a circle. Is that related to the 3-manifold?
Yes. There's a way of constructing these things exactly by sort of embedding your sigma in some degree maybe, and then sort of, yeah, exactly. Looking at a tangent bundle, put in spin structure on that's sort of induced from the spin structure on this, and then yeah, absolutely. I think that construction is maybe Kirby wrote it down. I think there is a way of understanding these things in a bit more of a uniform way. Yeah. Probably. So number fields, you also have bilinear forms, and there are 2 of them that are natural. And they're natural because they sort of give you analogs of both the linking pairing and the intersection form. So you don't just get one, you get many. So the linking pairings are actually maps. Use a number field and see class group. Maps from the dual of the class group. Mu equal to roots of unity, okay? So how are these things defined? If you have a pair alpha beta in C check M, answer it with mu, that's really equal to the homomorphisms from C check or from C to mu mod M. Then Kummer theory gives you that alpha and beta have associated an X and a Y in K star, which are both M powers. And you can choose them to be co-prime. Then what you do is you define this linking form. A beta, so M is defined as beta evaluated the divisor of X divided by M. So this is kind of exactly analogous to
You're using class field theory along with Kummer theory, right?
yes.
Like that's a cohomology class, an unramified cohomology class with values of mu, I guess.
Once you can also define it like this, just in terms of functions, that gives you something that looks more like that Tate bound pairing for curves. And how do you define where a function or f evaluated the divisor is really defined like this? Setting so product of f bar bar b. Star and d is equal to sum. The divisor and where star bar is like the reduction to the roots of unity. Okay, that's enough thinking about this. By reduction of roots of unity, I mean if f is co-prime to d, this is going to be a unit. You can take its value in the sort of residue field, and then you can raise it to the power size of the residue field minus 1 divided by n, and then that's going to be isomorphic to the roots of unity in k, so you get something which lies in. It's really independent of. Okay, so you have a bilinear structure like this that gives you something that looks like the bilinear structure you would expect in a 3 manifold. That's our linking pairing. For the Vey pairing, I don't want to say too much about it. The intersection pairing, all good. Also a kind of concrete description of this, but I'm gonna say that these are maps omega m from check m, check m to m. Again, m some divisor of the size of the groups of unity. C naught means so it's like the S class group where S is just 2. So it's a class group with primes above 2 inverted. So we can construct these things. And I'm just gonna skip the full definition and just give you an example. And that's it is basically the skew symmetrization of this pair. Whenever this makes sense. In other words, it's something like this. Reduction. So in other words, if you have a class in sort of MD torsion in a class group, maybe 2 classes like this, you can multiply by D and then take this, and then do the same thing for Y. Symmetrization is exactly the opposite of that. Just there's a more cohomologic way of defining these things by taking cup products, but I don't do. And the point about these 2 pairings is to satisfy a bunch of compatibilities. This is one of them. One is the skew symmetrization of the other, but they also satisfy a bunch of projection compatibilities or inclusion compatibilities between these levels. It's quite a long set of compatibilities.
It's sub MD.
Sub MD, yeah.
E.
M times D. D is some number, some integer. It's just it's kind of a you have to go up a little bit in order to be able to divide by D and get something in M. Of course, someone might say, oh well, Y is an MD. This you can define without having Y in MD, just because there's no need to divide by M.
For those 3 manifolds that come from, say, unit circle, unit tangent bundle of the circles, is there a compatibility like this as well?
I think if you have like a 3 manifold that's circle bundles fiber, like yeah, if you have something which is like fibered over a circle, I think there's some sort of and that would be the case for function fields, for example.
So from a little bit different about here is that so X and Y are in K cross and why are they both mth powers?
You don't need both of them to be M powers. You just need to actually it's just because
So maybe if you could like write that thing out as a cohomology group.
yeah, but maybe later. Okay, okay, so now I'm gonna write down what we found. That's sort of an analog of the story for instance. So our analog for spin structures is the following. The spin structure on the number field K is a pair I alpha such that I squared alpha is equal to the different the inverse difference of K. Up to scaling. Okay, so you would scale.
Where does I and alpha live? Sorry.
Oh, sorry, yes, this is an ideal. Okay, and this is an element.
Rational ideals. what do you mean?
Yes. So this is kind of like an equality of I squared. It's saying it's something that records the fact that the inverse difference is a square in the class group. In the world of Riemann surfaces, there's like a very close analogy with this. I mean, for a spin structure by ATS theorem is really a square root of the canonical bundle. So this is kind of just saying this is our analog. And so I think Mark will talk more about this, but there's a theorem of Hecke that tells you that every number field has a spin structure. So this is in Hecke's book. And so, every three manifold also has a spin structure. And so you're naturally have to wonder, well, what's the analog on the number field side of the story? And we can't quite get the full strength of the quadratic refine, but we can refine on stuff that a little bit sort of akin to the classic. Yes.
Can I think of pair as like a trivializing one co-bound grid for this inverse?
Yes. I mean, yeah. There are a couple of different ways of thinking about this pair. I mean, square root of the canonical bundle would be fine. Yeah. An element of the two-Selmer group of the field would be fine also. Okay, so here's our theorem. So each spin structure, we can associate in a not K invariant way. Two things. So quadratic refinement Q of the omega m's. So I'm just going to call it Q sub m. Class group. Quadratic refinement sub m of the intersection pairings, omega sub m's. But not exactly on the class group, but on something which is, or on the class group where it's mod with friends above 2 inverted, but on H1 C mu2. I'm going to tell you in a second. That is. I tell you what I mean by quadratic refinements. So that's our main construction. Almost get the refining bearings except for some blemish for the big. And so what do I mean? Quadratic refinement in this case. So basically we record all the things we'd like. So our maps, it turns out because of the compatibilities, we only need to sort of specify things at a certain number of sort of levels. So we have two maps. that so you have the first identity, which is that polarization Q is really this Q symmetrization, sorry, symmetrization linking form. Q of QZ is equal to twice ZZ. This is for Z. And then lastly, omega of X plus Y. X Y. Get to R X1. It's HC1. HC1 mu2 is our sort of unramified extensions of K that are split at 2 together with a splitting at 2. And sort of those naturally map into the class group with primes above 2 inverted by just forgetting about this bar. And so that's what this bar sort of represents here. That's what we're able to get in terms of structure. Okay. I'll just say a word about sort of things that go into there. Here, this thing here sort of gives you the hint that we'd like something that looks like the way the sort of leading pairing on 3 manifolds was refined. You want to find a way of dividing by 2 well. And so that's what we can do. You need some reciprocity laws to make sure that everything works well. What we need to use. And here we sort of refine it just following Mumford. So in Mumford's group, that dimension of mobile section of module was a refinement of the wave pairing. Sort of needed to go to quaternion algebras. What we do is instead we look at basically the second Stiefel-Whitney class of the quadratic form, which is given by trace of xy times. That gives us something that actually refines. Okay, so now I'll try to circle back in last 15 on what the implications of this theorem are for arithmetic statistics.
Can you just clarify that your theorem is for function fields or number fields or both?
Both. In function fields, sort of, there was already kind of a way, I think, of doing this. So somehow these bilinear structures would be packaged by sort of the Boolean pairing, and the way you would refine it would be by the term of cohomology. And these things match our constructions.
And there's not a claim that every quadratic refinement comes this way.
No. Even for 3 manifolds, not every quadratic refinement comes from the construction. Yeah, and I think there's a way of constructing consistency structures, and I think I don't think every quadratic refinements of linking consistency structure is. So by extensions in arithmetic statistics. So it turns out that you have a bunch of pairings, with levels and compatibilities. And all this information can actually be packaged in a very neat way in terms of by extensions. So, so all the pairings plus compatibilities packaged as a bilinear map with the metric map from C not check to new closures. This is a method by extension. What does that mean? Well, it means for every two elements in these groups, you get a torsor, maybe A sub X, let's say, or A sub XY. And then you're specifying all the automorphisms that make this sort of symmetric and bilinear. All the automorphisms of mu torsors. So as a little example, I want to show you how to recover maybe something that looks like a pairing, like a linking pairing from this thing. This informally. As an example, look at the linking, and what you would do is you would say you pick an XY. C naught check M. C naught check M. And then this torsor map gives you an A torsor like this. Okay. Now you would pick an arbitrary alpha in this torsor here. Then you have an alpha M AXY to the power of M. But then by using the structure of the bilinear of the symmetric by extension, that this is isomorphic to A sub X Y, which is isomorphic to A sub E Y, which is isomorphic. And so you get an element in mu, and so that gives you a map. It gives you a map. You check, and it only depends on choices up to mth powers. So this would give you a map here. Start with this, and you end up with an element. Okay, so that's fine. And now, how do you apply this to arithmetic statistics, or what can you say? So just some words about Cohen-Mansura heuristics. So the central question in arithmetic statistics is to sort of make statements about the probability that the class group or the P primary part of the class group of K is isomorphic to some finite abelian group G. So that includes, for example, so if you were able to answer this question, you can answer, for example, Gauss's class number problem. If you assumed some sort of independence with the different primes. And the sort of main answer to these questions in a heuristic sense were the Cohen-Mansura heuristics, which tells you an answer for this probability. And I'm going to disregard sort of unit rank and things like this, but or no, I'm not going to disregard. It tells you that the probability that the P primary part of the class group of that the class group is equal to some G is proportional to something like 1 divided by the number of automorphisms. U is the unit rank here, and they originally formulated it as K varies over quadratic fields of that unit rank. And this 1 over odd wing has become kind of a guiding principle for a lot of subsecond work. But there was a problem, which was it didn't explain the Cohen-Mansura heuristics you would see when there was sort of when there were roots of unity inside the fields you considered. So for example, at 2, there was a problem. And so this was fixed by Adam and Mallet, and then by subsequent work by Lipnowski, 7, and Zimmerman. But using our sort of packaging of this information here, it sort of suggested that we look at the category of sort of symmetric by extensions, and in fact, we find the following thing. So you look at SN extensions, then 1 divided by number of automorphisms on non-degenerate symmetric by extensions. It covers the Adam-Malley distribution. So this was a distribution that sort of described the behavior of class groups over families that all contained a certain root of unity. And so our main theorem, our main construction that we cited before suggests that we look at quadratic by extensions as long as you have a spin structure. Because if you have a distinguished spin structure of your family, that sort of distinguishes really one of the quadratic refinements of the bilinear structure you have. So it's actually gives you something that looks a bit like a quadratic by extension instead of a symmetric one.
You're looking at the same extensions of the same extensions of Q or of
Here would be SN extensions of some.
fix some field with roots of U.
Yeah, with rth. Yeah, exactly. This would be kind of with p to the rth, but not p to the rth plus 1 through serenity, and then it would be a symmetric, a non-degenerate symmetric z mod p to the r by extension.
What happened to the unit rank?
Yes.
You're looking at
This is after modding out. Sorry, this is Once the statement is like once you do a U push forward, you'll get the right thing. So this would be kind of like the universal thing in the sense of we recover the universal distribution.
extensions with
Yes. I mean we want things that are like where you don't have any Galois structure. The last thing I'll say is
But in this theorem, so you fix a spin structure in advance, right?
here, no, nothing.
You don't fix it.
No. So the spin structure comes when you want to fix stuff like monogenic fields.
Okay.
So so let me just say monogenic fields have a family level spin structure. And how do you see that? Well, the difference is always a square by Hecke. But for monogenic fields, it's also equal to the principal ideal generated by f prime. And so somehow you're distinguishing a spin structure over the family. And so it tells you that the category you should look at is really.
I thought you could extract square root of this.
Right. But it's a square root in the class group. And so somehow.
You need to choose an ideal I as in your.
Yeah, and that would be the trivial one in this case. So your I alpha would be 1 and then f prime of alpha.
Anything,
Yeah. And so our second theorem.
It's principle. Okay.
Yeah, exactly. That's right. That or again, sorry, like 1 divided by number of automorphisms on non-degenerate quadratic d mod 2 by extensions. And I'm going to say fixes Cohen-Lenstra for monogenic fields. Of course, this is like a hazy statement because what do we mean to fix? No one made a conjecture. But it sort of gives you all the results you find in the literature about sort of particular moments. And it also sort of matches computational data pretty well. Okay. And so as an example of the sort of numbers you get when you compare Cohen-Lenstra, Adam-Male, and our conjecture, if you look, for example, at the probability that you get Z mod 2 versus Z mod 4 versus Z2 cross Z2, in Cohen-Lenstra, it's sort of 3 to 1. In Adam-Male, it's 2 to 1, and in ours, it's 1 to 1. This is if you forget about roots of unit rank. That gives you a bit of the flavor of things. Thank you.